Well, thank you so much for giving me the opportunity to speak today, and thank you to the organizers for putting all this wonderful workshop on. So today I'm going to tell you about some work done over the last year and a half with various collaborators who I'll mention throughout. And the subject of this is quantum advantage in learning from experiments. And I'll tell you about what that means as we go through the talk. So let me start with a question, which is, what is an experiment? I think that often as physicists or as scientists, we sometimes take for granted what the notion of an experiment is. And actually, if you think about what an experiment is, it's actually a little bit less obvious when you go through different examples. So for instance, some examples of experiments include measuring constants of nature, such as the speed of light or the charge of an electron. It includes quantifying dynamical properties, such as the rate of a chemical reaction. It also includes inferring structural properties like the symmetry group of a crystal, or even learning more abstract information, such as the chain of chemical reactions that comprise photosynthesis, or whether Yang-Mills describes the strong force, or whether the black hole S matrix is unitary. With these different kinds of examples in mind, it really emphasizes that we should ask, what exactly is an experiment in its full scope of generality? Now, the goal of these papers over the last year and a half was to try to provide a information theoretic, and in particular computational framework for understanding what an experiment is. And I think that intuitively we have a sense that an experiment is something like an algorithm. It's some procedure that we do to learn information about nature. But in making this precise, we can bring to bear the tools of computational complexity to understand the resources that are required to perform experiments, and then show that certain kinds of experiments require more computational resources than others. So some recent perspectives on this problem include this beautiful paper by Huang and Preskel from earlier this year, in which they explained how many experiments can be thought of as quantum learning algorithms, which learn properties of partially uncharacterized systems via examples. Namely, that we have a system which is nature that we wish to understand, and we need to implement some learning algorithm to extract the information we so desire from nature. And in a related work around the same time, in collaboration with Dorit Aharonov and Xiaoliang Shi, we showed that all experiments, or we postulated that all experiments are examples of what we call quantum algorithmic measurements, abbreviated as QALMs, which are a hybrid of black box algorithms and interactive protocols. We'll talk more about what these things mean shortly. This is based off of previous work, or rather was inspired by some previous work in quantum computing and quantum information, which talks about interactive protocols. So what I'm going to be interested in this talk is the power of quantum memory. In particular, we would like to quantify the power of quantum memory in helping us learn about nature via experiments. So here's how to think of what I mean. Suppose that you have a quantum computer in your lab, that you're an experimental physicist, and that you have the ability to interface that quantum computer with your experimental samples. Are there any kinds of experiments or experimental protocols that you can do with the aid of the quantum computer, being able to couple it to your experimental samples, that you could not otherwise do? Could you do certain kinds of protocols that would be otherwise completely inefficient by any other method? That's what we're going to try to explore and establish. So we're going to distinguish between two kinds of experimental protocols, which I'll define in some detail. Those with a classical memory, which is going to be our model of contemporary and maybe 20th century experiments in physics, a model of when we take a course in quantum mechanics, what we usually think of what we mean by an experimentalist making a measurement and then interpreting the measurement data. We'll talk about this further. And then a more quantum type of experiment where we have a quantum computer in the lab that we can couple to our experimental samples. So we'll talk about this as protocols with a classical memory and those with a quantum memory. And again, we'll talk shortly about what this means. So let's begin with protocols with a classical memory. So we have here three different subsystems. We have nature, we have the lab, and we have our classical memory. We can think about nature as the system which we wish to interrogate, maybe some condensed matter system, something like graphing. Our lab is our experimental apparatus that directly couples with our experimental sample. It's our degrees of freedom in the lab which can directly interact with the experimental sample that we wish to inherit. And then finally, we have the classical memory, which we can think about as our laptop or a classical computer, which takes the outputs of the measurements and can do post-processing. It can store measurement outcomes and it can do computations on those measurement outcomes, which then can inform the kinds of measurements that we can make in the future. That is, we're allowed to work adaptively. In other words, we can use information from measurements that we've taken in the past to inform the kinds of measurements that we take in the future. So to be a bit more precise, and of course the coupling between our experimental apparatus and our computer is classical, but we only share classical information that we can store in our laptop. So the protocol is going to be formally in T different rounds, where each round is designated by a single coupling between the lab system and the nature system. There's a single interaction per round. And so the way that each round works is that first we prepare a state on the lab system, some quantum state, which can depend adaptively on what we've stored in the classical memory. So that as we initialize our detectors in some particular way. Then what we do is we query nature. We induce some interaction between nature and the lab system, which causes them to jointly couple, to jointly evolve. And then what we do is we measure the lab system with the POVM. If that's unfamiliar, just think about it as make some measurements, have some complete orthonormal basis, make some complete measurement on the lab system, which can depend on the classical memory, namely the way in which you choose to decohere the lab system, the basis in which you choose to measure can depend on information that you've collected in the past adaptively. And then what we do is we store the classical outcome of the measurement on the classical memory. And then we initialize the lab system to the all zero state and we start all over again. So again, just to summarize, what we do is we initialize the lab system, we couple nature and the lab, we decohere the lab according to some basis that we choose, or more generally some POVM that is designated by the classical memory, and then we store the classical index of the POVM outcome in the classical memory, which then informs future measurement rounds. Now, we'll talk about this in a specific example that'll make it more concrete. But then let's contrast this with the example of protocols with a quantum memory in which everything becomes quantum. Now here we now have like a quantum computer. We don't have to fully decohere any of the information in the lab. We can choose to store quantum states or quantum that we get by coupling nature in the lab. We can choose to store those states in the quantum memory for later use. And the entire protocol becomes completely coherent and completely quantum principled. So again, it's the same kind of protocol, but now there is no necessity of decoherence. We can do complete quantum computation on any information that we get by coupling our lab system to nature. So here we can imagine that we have the ability to couple to a full-fledged quantum computer, and then our apparatus can be completely coherent. So the goal in this talk is to find tasks, experimental tasks, for which there is an exponential advantage using a quantum memory versus a classical memory. Only the number of states or the amount of resources that we consume to perform an experiment when we have access to full-fledged quantum computation is going to be exponentially less than in the case of a classical memory. Let's get to the question.
When you say completely undecoherent, do you mean between nature and the lab, or is that decoherent? Like, can I have entangled states in the memory and nature, or is the lab decohering everything?
In the completely general case, I'll allow for everything to be completely coherent, both the interaction between nature and the lab and the quantum computer.
So that's an extra requirement for the lab.
Yes. So there are two parts to establishing this kind of exponential. Oh, yes, sorry.
Just what you mean by storing in a quantum memory is that you just don't decohere the quantum state that comes out, and you just swap it into some memory, and then you keep many outcomes like that in some memory.
For example, yeah, that is allowed. More generally, you can perform quantum computing.
Why is that not just a different experimental protocol? I mean, could I just subsume that under, well, I do more things before I decohere? I mean,
well, so I just mean that when we usually think about, so I'm just trying to have some means of comparison by what we mean by ordinary experiments and experiments in which you can really store and interfere quantum states. And I'm just saying in ordinary experiments, the paradigm is usually that you prepare a state and you measure it, and then you store information about the outcome that you measured, and then you prepare another state and then you measure it. You don't usually prepare multiple copies of the superconductor and interfere them. I mean, that's just is not what we do in ordinary experiments. But I want to see what the new possibilities are if we do allow for the ability to have multiple copies at once, for example. So we're going to explore that tension and that juxtaposition. So the two parts of this endeavor is to, on the one hand, show that a task can be done efficiently if we have access to a quantum memory, namely to show that it's possible to do it efficiently. And on the other hand, to show that a task that we designate is exponentially hard if we only have access to a classical memory. So that is, this first part is easy. If I have a particular experimental task in mind, I just have to demonstrate to you a single quantum algorithm, a single protocol, which achieves the task efficiently. But this part is hard, the second part, because if I want to show that something is hard classically, or by just doing, preparing a state, making a measurement, and repeating that procedure in an adaptive fashion, that we have to show that it's exponentially hard means we have to rule out all efficient classical protocols. So this is the technical meat, and in these papers is showing how you can rule out all efficient classical protocols, or these classical memory protocols, for performing certain kinds of experiments. So there's been some recent work in these directions, before jumping into examples, in terms of exponential separation, gated query complexity for learning properties of classical oracles, such as in the generalized Simon's problem or the welded tree problem. And these more recent papers by Huang Keng, Preskel, and Dorit, myself, and Xiao Yang about exponential separations in various kinds of query complexity. But what we're going to do in this talk is synthesize and generalize the approaches of three recent papers, Bubeck, Chen, and Li, Huang Keng, and Preskel, and Dorit, myself, and Xiao Yang, in which we provide a new framework for proving these exponential lower bounds for protocols with classical memories, namely showing that certain classical protocols are hard to perform. And this allows us to prove new exponential complexity separations between interactive protocols with and without quantum numbers. So let's proceed with a toy problem to get our feet wet, which is the problem of purity testing. So consider the following problem. Suppose that I have a source of a quantum state. And the way that it works is I push a button and I get a state out every time I query the source. And either every time I query the state, or every time I query the source, I get a maximally mixed state on n qubits, or I get a pure state. Now that pure state is going to be a Haar random state. But it's going to be the same Haar random state each time I query it. So I don't know what the state is. It's a pure state, but it's a Haar random state, but it's the same every single time. So I want to distinguish between the possibility that either my source is always giving me a maximally mixed state, or that it's giving me a fixed Haar random pure state. Okay? And the result is that the number, so the complexity, so if you do this purity test on n qubits and you have access to a quantum memory, you only need 2 copies of the state because you can do a swap test. This is why it's theta of 1. That's essentially the complexity. Just take 2 copies, you measure the purity, and you know which case you're in. But the interesting result is that even if you can work using any adaptive protocol, that the number of copies that you require of the states in order to distinguish the 2 possibilities is actually exponential. It's lower bounded. So just a side comment, in physics, sometimes we're often a bit sloppy about big O notation. This theta notation, in this case, means that it's actually, so big omega notation means we have a lower bound of 2 to the n over 2 measurements. And big O notation is like an upper bound. This means this is actually a tight bound. It means that we need at least 2 to the n over 2 copies of the state to be able to distinguish the possibilities of the mixed state source and the fixed random pure state source. But we can actually realize a protocol with 2 to the n over 2 copies that achieves the task.
What is n?
What's that?
What is n?
N is the number of qubits. So the proof of the classical lower bound, which is the technical meat, is around 20 pages in this paper. But by combining some of these recent papers that I described, we can actually reduce this to a proof that's only half a page long. And I will actually explain that proof to you briefly in a few minutes.
Are you assuming n is even?
No. Why?
No, the square root of 2 is a weird number.
Oh, yeah. Asymptotically, but yeah, sure. I mean, for large n. So, I mean,
I
whatever
thought you
you
said it was
realize.
exact.
What's that?
I thought you said it was exact.
This is an asymptotic result in large n. I just think that it's asymptotically upper bound and lower bound.
Leading order in large n.
Correct. Yeah. I just mean by exact, I should have been precise. I just mean it's asymptotically upper bounded and lower bounded is often what you mean by sort of exact. Let's talk about the learning tree framework for learning states. So suppose that we have access to a physical source producing a state row, and we want to learn about it in the setting where we don't have a quantum memory. So what does this protocol look like? So what we do is we obtain a copy of rho in the first round of the experiment, and we measure it using a rank 1 POVM. Now, for the moment, let's just imagine it's complete projective measurement that we, let's not worry about POVMs. Suppose that the BIs form a complete orthonormal basis of our Hilbert space. So what we do is that we take rho, we measure it in this basis BI, and suppose that the output is Q, which we then store in the quantum memory, namely that when we measure it by the Born rule, we end up in the state B sub Q, or when we make this measurement. So now in the second round of the protocol, well, we push the button again, we get another copy of the state row, and now we can measure in a different basis, B sub Qi. Now here what's interesting is that we can have our new choice of measurement basis adaptively depend on our previous measurement outcome. So that is, there's an index Q, which indexes the previous measurement outcome. So we can choose the basis adaptively to maybe make a better choice of how we want to measure things in the future, contingent on what we've measured in the past. So those are the outcomes R, namely that we measure the state B sub QR, and then we store R in the classical memory. Okay, so just to do this one more time so that we get the gist of it, for the next one, we obtain a copy row. We measure using the rank 1 POVM B sub QRI, depends on Q and R, both of the previous measurement outcomes. And then suppose that the outcome is S and we store that in the classical memory and so on and so forth. So one way of visualizing this kind of protocol is a tree. That we have a tree where here is the roots, here are the leaves of the tree. And in the first round of the experiment, we measure in this basis BI. And suppose that we measure the state B2, that this is what we observe when we perform the measurement. Then we go down the tree, we look at the descendants of B2, and we see that we should measure in this basis next. So this is this adaptive protocol. Depending on what you measure, you basically go down the tree, and then you measure in the next basis in which the tree branches off. So what you realize is that a particular instantiation of the protocol is a path through the tree, a root to leaf path through the tree specifically. Because maybe you measure B1 first, and then maybe you measure B12 next, and so on and so forth. You're going to end up traversing a path through the tree, which will correspond to your sequence of measurement outcomes. And the depth of the tree, the number of layers, if you will, corresponds to measuring T copies of the state. If you have T layers, then you've done T rounds of the protocol. So now, if let V naught through VT minus 1 be a root to leaf path through the tree, then the probability of taking that path, if I'm giving you the state row each time, so let B sub VT correspond to the state, which is at the vertex V sub T, then the probability that you traverse a particular path through the tree is the product over row sandwiched with the states in which you have measured it, where you take a product along the path through the tree you've traversed. And if you had instead the state sigma each time, then you would have the same expression, but you would replace rho with sigma. This would be the probability that you have achieved a certain sequence of outcomes in your adaptive protocol by traversing through the tree. So what we want to compare, if we postulate that, oh, it's difficult to know the difference between rho and sigma, then one way of quantifying this is by looking at essentially the one norm distance or the total variation distance between the two probability distributions, where we sum over all root to leaf paths in the tree. And we look at the difference of these two distributions. And essentially, if these distributions are extremely close, then we can't distinguish the possibility that we got rho every time versus we got sigma every time. So there are two strategies for showing that this quantity is small. One of them we call the edge-based strategy, in which we can bound the information the learner gains by traversing any edge in the tree. And in each round of the protocol, we don't gain that much information. There's a more global strategy called the path-based strategy, where we bound the information gain for traversing an entire path through the tree. So let's make this concrete in the example of purity testing, again, where we want to distinguish always getting a maximum mixed state in n qubits versus always getting a single fixed Haar-random pure state. So let me show you how the proof works. So, okay, so again, let V naught through VT minus 1 be a root to leaf path through the tree. And the probability of taking that path, in the case that I only give you the maximum mixed state, is simply 1 over 2 to the NT. Essentially, all paths to the tree are equally likely because the maximum mixed state is completely uniformly distributed. So, and the probability of any particular measurement outcome is uniform in any round. Now, in the case that we have a fixed but unknown Haar-random state, then what we should compare to is this product where we sandwich with a pure state psi I, but then we average over all choices of Haar-random states to reflect the fact that we don't know which Haar-random state we received. So there are essentially in this product, there are T copies of psi, and we average over psi because we don't actually know which psi we've received. We just know that we got one psi that was sampled randomly at the outset. And we want to compute this one norm difference. So let me just show you maybe very briefly what the computation looks like. So the one norm difference, it looks like this. So by a simple manipulation, so this is an identity. It turns out that at the cost of the factor of 2, this is an equality. If we only sum over the paths through which the probability of the mixed configuration is greater than the pure configuration, then we can get rid of the absolute values. This is just a simple identity of the one norm on probability distributions that you can show basically by the fact that probability distributions sum to the identity. But now what we do is we factor out P mixed, so we get 1 minus P pure over P mixed, and we would like to show that this quantity is really small, to render this entire sum small. But one way of showing that this is small is to show that the likelihood ratio, P pure over P mixed, is very close to 1. That's close to 1, and this whole quantity is small, and then that renders the entire sum very small. Okay, so we can compute P pure over P mixed, and essentially, maybe I'll just say briefly, by a series of relatively straightforward bounds, what you end up finding is that this quantity is extremely close to 1, and if you figure out what the implications are for the entire sum, we find that this difference, namely this sum, it only becomes order 1 when t is greater than 2 to the n over 2. So this gives us the lower bound. It's saying that this difference, that you cannot distinguish between these two probability distributions. There's not an order 1 total variation distance or 1 known distance between them. This is not allowed unless t is greater than or equal to basically 2 to the n over 2. That's essentially how the proof works for the lower bound. So let me tell you some, okay, sorry, that's not working. Let me tell you some other examples for exponential separations. Oh, here we go. Some exponential separations for in learning quantum states. So there's another version of this called polystate property testing, which ends up, so one of the issues with this distinguishing between a fixed Haar random state and a maximum mixed state is that if you want to do this in an experiment, you can't efficiently prepare a Haar random state. It's exponentially complex. So one thing which is nice is that, so let's consider this class of states, 1 plus epsilon p over 2 to the n, where p is a polystring. And suppose I task you with telling me what p is. I don't tell you what p is, you need to tell me what p is. So it turns out that even for this task, this state is efficiently prepared by essentially an order 1 depth circuit on a quantum computer. So this is efficient to prepare. The difficulty of ascertaining what the value of p is, it's efficient in the quantum setting, it's order n, but up to logarithmic factors, it's lower bounded by 2 to the n in the quantum setting. So this is an example where there's not these Haar random states involved, it's just this more ordinary looking density matrix, but yet it's still exponentially hard to distinguish between the different possibilities. Yes?
It seems funny this has a larger exponent than the Haar random case, which naively is more complicated, since here you were given much more information about this.
Yes, so one of the key things about this proof though is that, so in this particular proof, it is query efficient, but it's not gate efficient. So in the other, okay, so how do I say this? There's a different version of the proof in which there is a 2 to the n over 2, but it's also gate efficient. In other words, there's some trade-off between query complexity and gate complexity. Here I'm only telling you about the query complexity, but if you account for gate complexity, this protocol is actually is inefficient. But it turns out that there is a version of it which has a weaker bound for in which maybe I'll just push this, in which the gate complexity is efficient and the exponent is lower. And let me tell you a little bit about this. So in this variation of it, which I don't quite have time to describe, so there was a recent experiment that was done in collaboration with the Google Quantum AI division, in which they did a variation of this kind of identity plus epsilon poly over 2 to the n of figuring out what p is. What they did was that on smaller sample sizes, like on up to 8 qubits, they trained some neural net on some quantum data set where they made measurements on multiple replicas of these states. And they trained the neural net to basically output some information about this, what p is. And then they used this neural net to basically make a bigger neural net, which could then determine the answer to this question on larger system size. And what we found is when you scale up to a larger number of qubits, that you can efficiently determine information about p, even though the best known classical memory type algorithms are actually exponentially inefficient. So this is some proof of concept of how these bounds work. So let me tell you another example of quantum principal component analysis, which is given an unknown state rho whose top eigenvector is phi, and suppose that the gap in the eigenvalues of the top eigenvector and the second eigenvector, the gaps in their eigenvalues is order 1. Suppose that the task is given an unknown state, compute the expectation value of poly z on just the first qubit in the state corresponding to the top eigenvector. So another result from this recent paper is that by using a quantum version of principal component analysis, you can do this in order 1 queries. But if you would like to do this using only adaptive classical memory techniques, then it requires exponentially many queries. So let me give another kind of example about exponential separations in learning quantum mechanics. One is the symmetry distinction problem. So let me say it like this. The intuition is that it's difficult to determine the symmetry class of a strongly interacting quantum many-box system. So let's formulate a task in which this can be made precise. So let's first recall different kinds of time reversal symmetry classes of unitaries. Let's consider ordinary unitaries, orthogonal matrices, and symplectic matrices. And what the task is going to be, so this audience should be familiar with these three different kinds of unitaries, is that suppose that now instead of giving you a state each time, the way that this works is, that I provide a state, and what nature does is it evolves the state either by a fixed Haar-random unitary, or a fixed Haar-random orthogonal matrix, or a fixed Haar-random symplectic matrix, and it does the same thing each time. And I have to figure out which of the three symmetry classes is being realized by the evolution of my unknown quantum system. So it turns out that in terms of query complex, you can distinguish using the fully quantum approach between these three different classes, basically an order one number of queries. In particular, you provide a few copies of states, you evolve each of the states by the unknown unitary, and then you do some kind of swap test. And this ends up telling you which of the three symmetry classes are realized, at least in this context. But you can show that in the case where you only have the classical memory, that the best, you get an exponential lower bound where it's 2 to the n over 3.5. This is probably not a tight bound, but it's at least an exponential lower bound. And moreover, the protocol with the quantum memory is actually gate efficient. So let me, let's see here. I'm not sure why this keeps. Okay. All right. So there was also some version of this, maybe I'll skip through this, in which Google did some toy version of this. Of course, you can't actually prepare Haar-random unitaries in practice, but you can prepare random circuits, which maybe realize the unitary or orthogonal symmetry class. So that's what they did. And what they did was that they considered two different setups, one in which they were only given access to a single state evolved by a single unitary that they then had to measure, this setting with a classical memory, and then the setting of a quantum memory where they can make measurements on multiple replicas simultaneously. And then what they did was that taking this data, they did some unsupervised machine learning. They essentially performed some clustering algorithm on just the raw data. And what you find is that in the 1D setting, it can determine when you have the ability to make measurements on multiple copies that are stored in a quantum memory of a state which is evolved by an unknown unitary, then you can actually, by this unsupervised clustering, determine the difference between this random circuit which is built out of unitary, like ordinary unitaries without time reversal symmetry, and those which are built out of ones that have time reversal symmetry, whereas in the conventional setting, the clustering basically couldn't do anything. And we also did this for 2D dynamics, for 2D random circuits, and you can also, you see a similar ability to distinguish in this case, but not in the conventional or classical memory setting. And let me skip for the moment the way that this is implemented on the Sycamore processor. So let me explain one other kind of result which is conceptually different than the ones that I have told you about thus far, which is a stronger kind of result. So as I said, this is qualitatively different than the previous ones. And so let's now assume that we have a quantum memory. We're no longer going to compare classical versus quantum. We're going to say we have a quantum memory. We have a full-fledged quantum computer, but the number of registers that we have in the quantum computer is limited. Okay. So here's the theorem, and I'll say the theorem and then we'll unpack it a little bit. Any learning algorithm with k qubits of quantum memory requires at least 2 to the n minus k over 3 copies of rho to predict trace of p rho for all n qubit polyobservables p with probability at least 2/3. So what does this mean? Suppose I give you an unknown state rho, and I ask you to tell me all of the expectation value of all polyobservables p. Now there's exponentially many of these, so at least in terms of gate complexity, this is going to be exponentially hard. But what about query complexity? How many copies of rho do you require to extract this information? So the interesting thing is that if I have n plus k qubits, namely I have n registers and k qubits of quantum memory on which I can do anything, what it's saying is that unless k is equal to n, unless I have 2n total qubits, then this problem is exponentially hard. That if k, the difference between k and n, so I have n plus k qubits, and if k is less than n, then it becomes exponentially hard to perform the task in terms of query complexity, in terms of the difference between n and k. So in particular, so this combines actually all the proof techniques that I previously mentioned. And I should mention that this lower bound only becomes polynomial when k is sort of logarithmically close to n. But in fact, there's even a variation of this, of the above, which is gate efficient, where if I don't require that you tell me the expectation value of all of the polys, if I just tell you to do it for some of the polys, then there's a way of even making this gate efficient. So this basically tells you that there are certain kinds of tasks you can do with a quantum computer with bounded memory that you can't do with a quantum computer with a larger amount of memory. And that there, in fact, can be certain tasks for which these are sort of exponentially distinguished. So let me mention one last thing that I will conclude, which is the idea of k-replica quantum advantage. So suppose we want to learn some property of a quantum state rho. You could ask the following question: are there any circumstances for which the property is exponentially hard to learn if we only have access to k copies of rho at a time? So suppose that I give you k copies of rho at a time, and I say, you have to measure all those copies before I'll give you k more copies. But, so it's exponentially hard if you only have access to k copies at a time, but the property is easy to learn if I give you suitably more than k copies at a time. So in the context of this purity testing problem, the purity testing problem was easy if I give you 2 copies at a time because you can do a swap test, but it's hard if I only give you 1 copy at a time. So we could ask, is there a version of this with k copies? If I give you k copies at a time versus suitably more than k copies, is there any task which is sort of exponentially hard in one case or the other? So it turns out that in the k equals 2 case, well, we've already answered this question with this purity testing problem. The answer is yes, that there are cases which distinguish, actually, I suppose you should really call this the k equals 1 case. That if I have 2 copies versus just 1 copy, then one's exponentially hard and the other is easy. But it turns out that for k greater than 2, or maybe I should say k greater than 1, that it turns out that for all k, we were able to construct certain kinds of learning tasks for which learning properties of a quantum state is easy if you have access to suitably more than k copies of the state at a time, but it's hard if you only have access to k copies at a time. So let me conclude with some discussion remarks. So the usual paradigm of quantum advantage in quantum computing, when people talk about quantum supremacy experiments, for example, is that quantum computers are better than classical computers at performing classical problems that have classical inputs and classical outputs. But what we're talking about here in the context of what you might call quantum learning advantage is that quantum learning has advantage over classical learning for quantum experiments. Namely, in quantum experiments, the inputs to the experiments are quantum, either quantum evolution or quantum states. And even if the output is classical, namely the information that we ultimately want to get out of it is classical information, it's the case that in this setting, we can actually have provable, unconditional exponential advantages over more conventional experimental settings in which you basically just measure and in some adaptive fashion with a single copy of the state or unitary at a time. So what we've done is we've developed a new framework for proving exponential separations between quantum learning algorithms with and without a quantum memory. And we've established, in the very last part of the talk, what I told you about, is this first exponential trade-off between bounded memory and query complexity. Namely, that if you have a bounded quantum computer, then there are certain tasks that you can do with a larger quantum computer that you can't do with a smaller quantum computer. And there's an experimental demonstration of this quantum memory advantage in the NISC era on this, with this experiment in collaboration with Google. Now, something which is crucial to understand are what are the effects of noise. All the algorithms that I've told you about are sort of under the assumption that everything is noiseless, but of course that's not the way the world is. It would be interesting and difficult to see how robust these results are to the effect of noise. And finally, to find more physical examples in which we can imagine a future in which an experimentalist could and would want to have a quantum computer in their lab and be able to couple it to their experimental apparatus to achieve some useful advantages in practice. So with that, thank you so much for your attention and happy to answer any further questions.
Can you say something about the complexity of distinguishing a unitary quantum channel versus a quantum channel which you can decompute? It sounds quite similar to the mixed.
Yes, so indeed, so there's something that a task that I didn't say. Suppose you have the following task. Suppose that I either give you the maximally depolarizing channel, or I give you a fixed random unitary. That is also exponentially hard to distinguish in the classical memory setting, but is easy to distinguish in the quantum setting.
Yeah, I just want to ask a simple question. So what is the relation? I didn't quite understand why the quantum memory relate to the gate complexity, right? That's equivalent thing in your language.
Yeah, so there's 2 different kinds of notions of complexity in this case. There's the query complexity, which is like the number of states or the number of copies of the state that we require, the number of queries to the unitary that we require in order to complete the task. But then there's also the gate complexity, which is, okay, well, once we have those states, how many operations do we need to do on those states to achieve the answer? So what you can have is that you can have problems, for example, which are query efficient, which require very few states, but require essentially a lot of